pretty much what we're going to do a chapter of class. And then what we're going to do is that we'll assign the chapter, you'll go home and you'll read the chapter, and then what you'll do is you'll come up with 5 questions that you know the answer to. Okay, you'll understand that. And don't copy, because I'm going to check this. So if you copy somebody else's and you both have the same 5 questions, even though they're in a different order, what do I know? So it's going to be impossible for y'all. I can understand, and that's why we're coming up with 5 questions. So between the whole class, 5 questions, we should have different, somebody should have a different question about the project. And then what we'll do, and this is what I find out, this is the way the class works, so this is nothing new, is that we'll start off by you asking the class one of your questions. And then what we'll do, we'll see if anybody has the answer. Well, you're the one that's supposed to know the right answer, right? You understand that? And we'll go through the class, and you'll have an opportunity to ask one of your questions to the rest of the class. Everybody see how this is going to work? So how are you going to do that? You're going to have to read the chapter, right? You understand? So today, since we didn't do anything, we didn't introduce this on Monday, because I didn't know. So like I told you, I think I told you this is the first time I've taught the class. So, I didn't understand how the class actually ran, but that's the way it runs. So, introduction to technical drawing. And like I said, I have no idea why Nancy put subtitles on there. The name of the class is Blueprint. Right? Blueprint reading. So what we first need to do is try to figure out what a blueprint is. Anybody know what a blueprint is? Nobody in here knows what a blueprint
is. It's like a diagram, a design.
Yeah, but it's got to. If people still refer to the prints that we see today, especially the old school people, refer to them as blueprints, even though blueprints are basically obsolete. The only thing we see blueprints now are for nostalgia, you know. So you can find a blueprint of the Enterprise. Well, when the Enterprise came out, blueprints had been long past being used. But there's always been the need of making copies. If I was going to build a building, and I've got plumbers, and I've got electricians, and I've got these and these, you know, and every one of them needs a what? They need a print of what's going on. Well, copy machines have not, and inkjet printers and plotters have not been around since we started building buildings. So back in the 19th century, the 18th century, there was a guy that figured out he could coat paper with a certain material that came from a tree, and it was licensed. So what that meant was, if they exposed this to light, it changed colors. And guess what color it changed? Blue. So what they figured out is they could lay stuff out on the paper and expose it to light, and then everything would turn blue except for what was covered up. And then they would take the paper and they would wash it, and that would wash off the material, and then you would have a permanent copy. Now over time this evolved, of course, where they would use like plastic or glass or something, and they would put their print on something that was transparent, and then they'd lay it on this paper, right, understand, hang it up outside, right, on basically a clothesline, bring it in, right, wash it off, and now they can make how many copies of it? As many as they need. And some of them do it just opposite. So this is an example of a blueprint. And we still do them every once in a while. This is the Wright brothers plane. And so they can make as many copies of this as they wanted, they needed, and give it to everybody that was involved. Of course, now they're obsolete because we have these big old plotters. Another problem we have is a lot of the prints, we don't like using little old tiny prints, right? They like these, what they call D-size prints, and I'll look up the size on that. But these things are probably as wide as you can stretch your arm, and they're probably that big. right? And that makes the prints real big. You've probably seen them once in a while on the movie, but architects will do what? They'll roll them up and carry them around. They're real, real big. Makes it real easy to read. Well, now we have copy machines that can make prints. And we have plotters that come up and actually plot. And when they first came out, they were big plotters, and the paper actually moved across these spools, and they actually used ink. And they would come in, and the ink pens would actually draw the print. Now we got copies that can make these copies. So basically now we have what they call white prints. You're going to hear a lot of people refer to these things as prints. I'm sorry, blueprints. In fact, the book still calls it. But the blueprints today are not made like blueprints was then, right? They're either made on a large copy machine, or they're done with some type of scanner or something like that. What is a symbol? So nobody knows what a symbol. We deal with symbols all the time. When you drove here today, you saw a bunch of symbols, right? Well, what it is a shape, or it's an object, right? A picture, basically, that represents something else. Okay, you understand? So a stop sign is a symbol. Right? What does it represent? Well, it tells you to do what? Stop. Right? But instead of writing out the word stop, we have a problem. For one thing, everybody in the world does not speak the English language. So a long time ago, they came up with a group of what they refer to as international symbols, which means certain signs will have certain shapes. And then certain shapes would, and so if we see a triangle, it means it's some type of caution, right? And then they'll have a car on there with squiggly lines, and we know that means slippery when wet. Well, they don't have to write out slippery when wet anymore because that is an international symbol. So what that means, it's been approved by ISO. So if you're driving over in England or over in Europe or, anywhere you drive just about in the world that recognizes the international symbols, you know the sign for slippery when wet, right? You understand? Because they're what? They're the same. They're international symbols. So symbols, a symbol is an object that represents, stands for, or suggests an ideal, visual image, belief, or action of material entity. This came off the internet, by the way. I just looked up and said, define symbol. This was a real good one. I enjoyed this one. You can find just about anything you want on the internet. I'm laughing because of the people that hacked into what was Ashley, where they had that site where spouses could cheat on their spouses, and somebody hacked into it, and they released a bunch of names today because they didn't take the site down. So it's going to be interesting. Maybe they'll let us know who that does. Are we okay? Okay. So these are symbols. These are traffic symbols. And these are basically international symbols. So we would see this just about anywhere. That also, if I went into Mexico, we would have no problem with traffic signals. If you went up into Canada, you'd have no problem with traffic signals, right? Because these are, as long as the country has adopted the ISO symbols. ISO is International Standard Organization. Of course, that's what they try to do. They try to set standards that different countries use to make it easy on everybody else, right? Are you okay? These are road map symbols. So, when we drive out there and drive, and road maps are, my wife still likes to get them, but, most people have GPS either on their smart device or have a GPS on there. But they still use symbols to represent things, right? While you're driving along, things will pop up on your map there showing you. So you got to understand these symbols if you want to read a road map. You've got to understand, and a lot, when you take your driver's test, you drive around, but the written test is basically what? Anybody take a driver's test lately? The written part? Anybody remember what was on there? Mostly symbols. On your driver's test, most of them were symbols because that's what they're trying to say. You get out and drive, that's one thing, but you got to understand the symbols of the road, right? Nobody remembers what the written part of the driver's test? I do, and I have good graces. I started driving Y16. These are symbols that they discuss in the textbook, and we're gonna. The book is going to look at electrical symbols. The book also looks at piping signals, fluid symbols. I can't remember. And we'll probably add some electronic symbols in there, so we'll cover a little more than what the textbook does, because a lot of y'all are in electronics and need to understand these symbols. The symbol that they bring up in the textbook, and this is on page, first page, in fact, is the symbol delta. So the Greek language has been around for years. And the Greek language consists of a lot of symbols. Okay. Consists of a lot of symbols. And it's obvious that, since these symbols were out there, it would be obvious that it would be moved into our scientific community, right? The only symbol that they talk about here is a symbol that they refer to as delta, Greek level delta. In electronics, we use this symbol for amplifiers. That's an operational amplifier. We use these symbols for devices called diodes. We use a symbol for a device called an inverter. We use a symbol for a device called a buffer. We use this symbol, a variation of the symbol, for what we refer to as earth ground. We use a variation of the symbol for something that we refer to as common. And I'm sure there's a few more. Especially in electronics, we use this delta symbol a lot. The Greek symbols, just the ones that I can think of. We use a lot of, we use this symbol right here in electronics. Oops, sorry. Oh, she don't have that enabled. So. This is omega. We use this to represent the amount of opposition we have in an electrical circuit. We refer to it as ohms. But that's a Greek symbol. Some of y'all have probably seen this symbol right here. This stands for micro. We use that to allow us to decrease the size of very small numbers. Okay. So if we had a very small number like this, then we would refer to that as 10 micro. So micro is to the -6, which means you come over here and move it over 6 places, and then now we can call that micro. So 10 micro, if you understand what the symbol micro stands for, it's a lot easier to say 10 micro than it is to say 0.00001, right? You understand that? Milli, that's not a symbol, that's just an E. Kilo is K, so those are not really symbols, those are more of abbreviations. A micro, a mega, this symbol right here, we use this in electricity, and y'all probably seen that before. That's the symbol for infinity. So, and we use it for positive infinity and negative infinity. So basically, that means somewhere out there in time, positive and negatives touch together, right? I don't know, but symbols are very, 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 very important, especially in the trade. So every trade has symbols that they use to represent things on blueprints. Because I can't draw pictures, right? You understand? Because pictures take up a lot of words. But if I understand what a symbol is, which is a small little diagram of a picture, it's not really a picture, it's a drawing, then we can we can make our schematics and stuff very, very small compared to what it would take if I tried to draw a picture of everything that was in the circuit. So what is a schematic? So this is in page 4 in the textbook. So what is a schematic? It's a line drawing. There's a lot of things that can be a line. So we got to refine that a little bit because there's a lot of things that can be line drawing.
Made for a technical or scientific purpose.
Like you got that right on. Book basically leaves off a line drawing made for technical and scientific purpose. And I'm the one that added utilizing symbols because that's what a schematic is. But what we do is we have lines. So every one of these schematics have lines. But then we use symbols to represent other things besides lines, right? You understand what I'm saying? So there's actually, in your textbook, it actually gives you, no, this is not it. So basically, schematics. If you're going to work in a technical trade, then the drawings you give that shows you how things work, where things are placed, how things go, are going to be drawn using symbols. If you don't know the symbols of your trade, right? So if you don't know all these symbols in the traffic system, you will not pass the written test. You have to pass the written test before they let you take the driving test. Right? You understand? Because they say, okay, if this person doesn't understand the symbols of the trade, he doesn't know traffic is merging, he didn't know when a stop sign, they don't know anything about how to drive, so they're not going to put that sucker behind a wheel because they don't understand the symbols of driving, right? And that's true for any trade, any craft. Every craft, they gotta, except maybe artists, freehand raw stuff. But every real technical trade, let's put it that way, every technical trade has symbols so we can write things down and we can put things down on paper. It's just like algebra. We use symbols all the time in algebra, where we let A represent a number. Right? We don't write the number because what they're saying, A can be any number. You understand that? And it would always be A is equal to B plus C, right? Well, B is representing a number and C is representing a number. It don't make any difference what the value B is and what the value C is. A is equal to B plus C, right? You understand? So no matter what B is and no matter what C is, A will always equal to that. And that's what algebra is. So algebra is a mathematical language, but it uses nothing but what? Symbols. When I was in high school, I did not do very well in algebra. When I got into the Navy and they decided I needed to go into electronics, then the symbols made sense to me because I understood what A is equal to B plus C actually meant, right? And what rearranging the formula. So when I got into college, I aced every math class I ever took because now the math made sense. Now the symbols made sense. So symbols are like speaking a language using symbols. Symbols are connected using lines to represent a system. You cannot understand somebody unless you speak their language. The word schema comes from, and this is out of the textbook. So a lot of things that we do come from the Greek or the Latin language. So in Greek, schema means to form, and schema means a figure. Modern definitions of the line drawing made from a technical or scientific purpose. Using symbols. I need to add that to that. Or utilizing symbols. So this is what the textbook talks about, the definition of a schematic. And it splits it into 5 parts. So number 1, a schematic is a line drawing. Everybody okay there? Number 2, it's made for scientific or technical purposes. We would call it probably on the technical side in what we teach here. But if you take math or biology, You know, your formulas in biology deal with symbols, right? You understand that? Shows how a system works. So we'll look at the device itself. I have a couple things up here. The device itself, and then the schematic used to represent that device. And until you learn the symbols, it won't make sense. But you'll see it's a lot easier to look at the schematic than to look at the device itself. So from troubleshooting purposes or wiring purposes or constructing purposes, we build things with symbols. You know, if I was a carpenter and they tried to draw a picture of a 2x4, and I'm trying to build a house, how big would my prints be? Or if I'm a plumber and they tried to draw the pipes or put pictures of the pipe, how big would my prints be? Right? And then if they change the style of pipe, you know, or something happens, they would have to come back and retake all the pictures, right? But if we use a symbol to represent a pipe, in a ledger somewhere, all I have to do is mark out what it was and put a new thing in there, right? You understand? Which would be a lot easier than trying to go out and take a bunch of pictures. Symbols are used instead of pictures. The symbols are connected to show how the system operates. They reduce the complexity of the system to a manageable drawing that can be understood. But it can only be understood if you know the what? Symbols. That makes sense? Any questions? So this is a schematic using electronic symbols. Simple, these are very simple electrical schematics. And I wish we had a picture of the actual thing. Let's see, this is a simulation that we use in troubleshooting. So if you take the troubleshooting class, we use a software application that allows us to troubleshoot. On the left is a picture of the actual circuit card, and then on the right is a schematic. What the schematic does, the schematic is laid out in electronics. The schematic is laid out to show you the logical operation of the circuit. It's not laid out to show you the placement of the component. You understand that? When I'm an engineer and I'm placing components on a printed circuit board, what am I trying to do? I'm trying to save space. Why am I trying to save space? Space is what? It's money. Space is money. The bigger the printed circuit board that I make, I understand what a printed circuit board is. Everybody okay? But when they're laying out the printed circuit board, they're trying to make it as small as possible. When they're numbering the components on the printed circuit board, they usually start at the upper left-hand side and go across, so that means the numbers are grouped together on the schematic. They don't have to be grouped together, right? You understand that? So resistors have numbers, and these are all self-printed on the printed circuit board. Hold on, let me go get one. This is a card that allows us, because it's sensitive to static. So when they make the printed circuit board, they try to make it so that it's going to be as small as possible. When they do the schematic, inputs on the left, outputs on the right, so that we know that the system flows from left to right. So that's what they're doing on the schematic. They're trying to make it easy for us to figure out how it works. So this is neat, you know, seeing the schematic, but what we got to understand is to place the real device, and we have this in lab too, where students are trying to wire up these circuits from a schematic, and they try to make it look like the schematic, and then they end up using a lot more wire than they would if they didn't wire it accordingly. If they wired it electrically. And another thing, of course, is how much wire you put in a system. We teach a class called motor controls, and we have to wire. I think Mr. Baker, you had that. Yeah. We try to wire that thing. Yeah, James, you've had that too, right? You hadn't had it yet, have you, Greg? Well, you hadn't had it, have you? We try to wire up circuits, and what we're trying to teach these people is to try to wire the thing with the minimum and the shortest wires that you possibly can. And why we're trying to do that? Because, you know, you get out in the field and you're given the job to wire something, and you're using, 15 rolls of wire. This company over here is using 5 in exactly the same circuit. What's going to happen? I mean, somebody's going to be out of business, right? You understand, real fast, because either this guy's going to undersell me, giving me the same thing, right? Or he's going to make, or he or she's going to make a lot more money. Well, we had a friend, my neighbor, got his journeyman's license, and he went into business with a contractor, and he bid a job. And he's no longer in the business because he didn't know how to bid. He didn't bid the job. He didn't bid the right amount of wire. He didn't do it right because he didn't understand that technique. Are we okay? So the one they show you in the book is 1-3. This is not really an electronic schematic. What the drawer is trying to do is trying to make it associated with electrical schematic. This would be electronic. Normally in electronic powers, on electronics, we don't show the source of the power. We use a symbol to represent the source of the power. Make sense? I can't read this. I don't know where Nancy got this, but this is a schematic. Can y'all see that okay? And these get really complicated, but these are the symbols for capacitors. This is a symbol for a switch. This is a symbol for a resistor. This is a symbol for a variable resistor, kind of like you would use on a light dimmer if you got a light dimmer in your house. This is a symbol for a Zener diode. But to us, it don't really make any sense unless you understand the wrong symbols. But from my point of view, if I wanted to fix this system, if I had it broke, and I didn't have this, if I didn't have the schematic on the thing, you're in trouble. Because there's no way in the world I can look at the components and trying to figure out how they're electrically connected. And it's hard to. We had a system out of U.S. Steel. We had a circuit board. We didn't have a schematic for it. So we used a device called an ohm meter. Conductors should have almost no resistance at all, or it doesn't have any opposition that we can measure. And then what we would do is we would take our ohm meter and we'd put it on one of the devices, and then you'd have to go over the entire card and touch everything, every pin, until you got no ohms. Luckily, the meter beeps at you when it sees that, so you didn't have to look at the meter. And then you would draw a connection there. And then you'd keep refining it because things would shift around, right? Understand? And it took us a long time to do it. We finally did it, but it was a process that took a real long time. And then once we got the schematic, still there was no 100% guarantee that our schematic was exactly the same because we might have missed something, right? Understand? Then we had one schematic we got in for an induction heater, and it used a bunch of digital circuits, and every digital circuit's got its own symbol. Well, the draftsman that did this used the same symbol for everything. And so some of them was right, and 90% of them was wrong. Undoubtedly, he or she only had 1/10 of it on there. And we literally had to pull the boards out and find the part numbers, look up the part numbers. And when we looked at it, it was obvious. I said, you say, there's no way in the world this thing could ever work. So that created a lot of work for us because why? The schematic was right, but the symbols, so the lines were right, but the symbols were wrong. So what we had to do, we had to pull the boards out. We had to find U104. We had to get the part number, look up the part number so we would know the symbol. And then we had to come back and redo those whole prints because there's no way in the world we could have troubleshot. And we didn't know it, by the way, until it broke down. It was an induction heater. An induction heater, this was, the place was called the Curve Master. And what they did, this was in Inslee, when Inslee was still running out of U.S. Steel before they shut it down. And what they would do is they would heat temper the crown of the rails. So when it goes into a curve, they have to use different tempering on the top crown of the rails than they do on the straight run. It should make sense because there's more stress on the tracks when the train's going in the turn. And boy, that was fun. And we went from MG sets, motor generator sets, where they had a motor running a generator, generating the right stuff that was needed for it. And then they replaced it with solid state units. The problem with the MG sets were they were kept in, I can't remember, either helium or something. So that meant that when they broke, we couldn't fix them. So they had to ship them off on a big 18-wheeler because we didn't have the ability to go in with that gas inside that unit. So that's why they replaced them with solid state units. So when they broke, we could do what? We could fix them, and they didn't. But not with those prints.
There was some interesting stories on that when we installed that.
This is a diagram we call a line diagram, and they have a picture of one of these in the textbook on page 5. This is not the same one. This is a schematic that if you take the motor controls class, we deal with this. And then the textbook that you do, if you take motor controls, it will tell you the symbols and everything. And then the book shows you, and then we actually pull up a set of real good prints. I should scan this one too. Just as an example of standardization. If everything is standardized, that means I can do what? I mean, I could work for U.S. Steel and look at these prints and I can figure out how it works. I could go out to CMC or Gas Stump or any place that still uses these guys, and then I would be able to troubleshoot. This is truly electrical. This was back in the old days, everything was hardwired. I mean, everything was wired up. As time went by, some smart people, and microprocessors became very, very popular. Some smart programmers realized that we could replace the decision-making portion of this diagram with a computer. Because 90% of the control system is decision-making. Did this person press this button before that button, or after this button? Is this guy true or false? And that kind of stuff. Computers love that kind of stuff. So they came out with a unit called a programmable logic controller, which is nothing but a computer. But guess how you program it? You program it using this language right here. Because why? Because they're trying to bring a computer into a system where the electricians understand this, but they don't understand computer language. They don't understand. You know, if you went over here and looked at a program for these robots, electricians go because it's a text-based language. But PLCs, you program in what we call ladder logic. By the way, they call this a ladder diagram. Can you see why they call it ladder? Because it looks like a ladder. It looks a lot like a ladder. So this is one that you'll actually see if you take the motor controls class. But if you look at the one in the textbook, they use the same symbols, right? You understand? So this is out of a textbook written by somebody at the Schoolcraft, and this is actually a print at number 4 galvanizing line, which has been shut down out at U.S. Steel. And that's shut down the blast furnace. Good gracious! Yeah, I know it's a blast. All the pictures they're showing on TV is not the blast furnace. Most of them are showing the pictures of the Cubot furnaces where they actually make the steel. The blast furnace is where they make iron. And they use iron to make steel. So they're not going to make steel out there anymore. They're going to melt steel. So they're going to replace the Cubots with what they call an arc furnace. There's going to be schematics for the arc furnace, right? So these guys will know how to look that up. But they're actually going to melt steel. They're not going to make steel. It's a lot cheaper to melt it than it is to make it from scratch. How many people they say they're going to have working out there? So this is going to cost about 1,100 jobs, and they're going to have about 700 people working out the plant. When I worked out there was 10,000 people working for USC with all the plants that used to run out there. So we'll look at these symbols. So we're not trying to learn this, but this is what we're going to do. We're going to look at symbols. So the rest of the chapter, what we're trying to do with this chapter is just trying to get an introduction, right? You understand? And then we'll have individual chapters on the symbols and then diagrams. And then we'll try to add another one in there where we're going to look at electronic symbols. Some of y'all are in the electronic trade, you know. Some of you are not. Any questions so far? Any comments?
What did you say those lines on that board was? You see them.
We call them traces.
Traces.
Some people call them foils, but I learned them as traces. And those are the actual conductors. So in electricity, what we have to do, and they talk a little bit about this in this chapter, is that the electricity works a lot like the human circulatory system. How does that work? So what we got? So the heart don't make blood. What does the heart do? Pumps blood. That's already there, right? Okay, and it pumps it out through our system. Who makes blood? Liver? One of those organs, mate. Huh? Bone marrow filters it, right? But don't actually make it. I don't think. It don't make a difference. Pumps it out, and then it goes through the muscles. So the blood is the power source in your body. So without blood, you're going to do what? You're going to die. So the blood is the power source that powers your muscles. It delivers oxygen to your muscles, and it also delivers, nutrients and everything. Once it goes through your muscles, what do? They bring it back through the lungs, comes through the lungs where they add oxygen to it again, then it goes back to your heart. So a basic electrical system, very easy, consists of some type of pump, and then we take it through conductors, then we go through some type of load, and then we bring it back here. So this is why everything you plug into electricity has two wires. Right? One of those wires gets broke and nothing works anymore. So what we're doing is we're pushing something with a pump through some type of piping, which we'll look at later on, through a load. So all the piping does is deliver the nutrients to the muscles, right? You understand? The muscles is what do the what? What does the work? So your blood is the power source for your whole body. If your heart stops working, you die. If you lose an artery or something like that, and your blood can't make this path anymore, you do what? You die. Electronics, if you lose one of these lines, then the system does what? Dies. And we break this, we don't do it on our heart on purpose, but we break this on purpose, which gives us the ability to turn things on and turn things off. So we can turn these lights off. I go over and flip a little switch, and all I'm doing is breaking one of these lines. If I break one of these lines, I have no flow anymore, right? You understand? And the lights die. The lights die. So what they're doing is the two lines on this schematic, these are your two power lines out here. And then everything in here, and this is the way we control it, and then over here, these are the loads. And everything between here and here, this is how we control it. So that would be like a light switch, right? When you come up here and you flip a light switch off and on, you're controlling the lights. The lights are the load, right? You understand, but you need to be able to control that. So that's on basic electrical circuit. We'll look at some of the symbols. So we have different symbols for the power source, the source of the push. These are some electrical diagrams. So if you was an electrician, this is not in the textbook, by the way. This is, if you take commercial wiring, if you take the commercial wiring class, you will run into these guys. You'll get a copy of them in the textbook. And these are prints that an electrician would use to figure out how to wire a building. And it's just nothing but a bunch of what? Lines and symbols. And it tells the electrician a lot of stuff about how things work and how things are supposed to be done. If you can't read this, then of course now you're going to do things that the architect and engineers that designed it did, right? And it might not work the way they expected, or it might not be the way it's supposed to do. Just like me as a plumber, you know, if I didn't understand piping and how to route that, and I pull my pipes up over here, and they want to put the commode over there, then we got a big problem. What will probably happen? Yeah, the plumber will have to come back and make good, and they're not going to pay the plumber anymore because the plumber bid on the job, right? You understand? And it's not like the U.S. government in these big places that makes these big airplanes and stuff where they factor in a cost overrun. I mean, if you're a contractor or working for a contractor and you bid a job, then by George, that's what that contractor is going to do what? Going to pay you. And if you screw up, it's on your bill. Kind of like the guy on Jurassic Park. What was his name? The computer programmer. Screwed up his code and he was complaining about cost overruns. This is a print for a, we have two versions of this. I should have got the other one. We got one that's in a blueprint. And this would be a white print, right? This is what we run into now. Even though most of your people that you got in there, they're going to call this a blueprint, even though it's not a what. So normally we use the term print, but you'll be surprised on these. A lot of people still refer to these as the blueprint. So this is the blueprint for the outside top section of the Enterprise. And they got a version of this that is a blueprint. So now when we see true blueprints, it's usually for nostalgic purposes, right? So you can find a blueprint for your iPhone. Odds are when they built it, they didn't use a blueprint, but they converted it over just because. It's like some directors still make black and white movies. This is a schematic. And by George, if you don't understand symbols and you get into this guy, then you're going to have big problems. But for somebody like me, because I know the law, I know all the symbols, people want to call and want you to fix things all the time. And you say, well, you know, I'll look at it, but if I don't have the schematic, you know. And a lot of things are getting so complicated and so cheap now that a lot of times they just replace them. So I almost bet if you fry a circuit board on your cell phone, and you've got if you got insurance, they'll replace it. But odds are they don't send that thing off to be fixed. They just probably just want to throw it away. TVs are at that price. You know, used to they were when I was young. They had people that fixed TVs all over the place, and we used to teach TV repair. But now these things are so reliable because they're put together by robots and manufactured. Usually by the time a TV goes bad, you've been waiting for it to go bad anyway, so you can do what? Buy a new one. Yeah. No, I wish that thing would go out so I could buy me a new one. So I have a reason to talk to my spouse about buying that. This is a this is a drawing of a direct drive for a motor. Here's a motor over here. This is a 3-speed motor. And you can see a lot of times to aid us with figuring out the symbols is they write little things on here. So I know this is the 3-speed motor. I know this is a motor. First of all, it says what? Motor. And then it has this wire. Can y'all see what that says?
HIGH, what does that spell? Nobody knows what HIGH spells. That's high. That's MED for medium and low. So sometimes what they do is they actually put annotations or lettering on the schematic to aid people to figure out how the thing works. Okay, gang, I'm going to pause this. Y'all go ahead and take a... What's the first thing usually the doctor does when you go to the doctor for a checkup? Checks your blood pressure. So to cause things to move, we've got to have a difference of potential or a difference in pressure. So wind blows from high pressure to low pressure, right? Water flows downhill because the gravity down here is bigger than the gravity right there, right? So things move between high pressure and low pressure. So if I'm going to have anything that flows, I got to have a difference in pressure. And that pressure for the human body has to be within a certain range, right? You understand that? So if you have high blood pressure, they're going to come up and they're going to try to give you something to lower it. If you have low blood pressure, they're going to try to give you some kind of medicine to raise it till you get into that legal level. Well, in electricity, our pressure is created by something called voltage. And y'all probably familiar with voltage, right? And when they give you the amount of voltage, that is the amount of pressure that we have to cause things to go on. So different things are designed to operate at different pressure. If I give it too much pressure, it's going to burn up on me. If I don't give it enough pressure, it's not going to work. It's not going to create enough power to do its job. So what we have is we have devices where we can have one pressure that's a little high, and then we could use it to lower it to the right pressure that we have. So out here in your car, USB is 5 volts. That's the 5 volt pressure. But I can go out there and I can get a little unit and plug it into my cigarette lighter, and then I can plug a USB device on there. Your car system runs around 14 volts. And then when it's sitting static overnight, it runs 12 volts. So anybody says it's a 12 volt system, it's not exactly true. But I've got to give that USB, I've got to give my cell phone 5 volts. So I've got to have something that gives us a pressure. So even though the input is changing, it can be anywhere from 14.3 down to 13, about 12 volts. I got to give something so my cell phone that's what? 5 volts. So we use a device. One of the devices that we can use is something referred to as a Zener diode. And that's what a Zener diode is. It's a voltage regulator. So I can come over here and I could have 12 to 14.3 volts over there, and I'm going to put that resistor, that's a crummy symbol for a resistor. And then I can come over here and use a Zener that's rated at 5 volts, and then what goes out here is plus 5 volts. So a Zener diode is a regulator. That's what it is. It's a voltage. Somebody asked that question. That's why I'm answering. So a Zener diode will let us take a voltage that's don't stay the same all the time, and then we can go through a device called a resistor and put a Zener diode out there by George, and it's going to give us what we call a regulated voltage. Regulated voltage is a term we use when we say it stays constant even though you have varying conditions. So it's kind of like speed control in your car. It's a regulated system. And that was one of the diodes. That was one of the symbols that was on that electrical schematic. By the way, the true symbol, if you look at the symbol should be colored in. Because if we see this symbol right here, this is the symbol for a common. So that we don't get the symbols confused with each other, the common should not be colored in, and the diode should be colored in. So, but it still uses the Greek symbol for this.
So can it be pointing in any direction?
No. And that's what you'll take that and you'll have to take. We're not going to teach. If you take solid states, if you're in electronics, we teach you how to design a Zener regulator power system. We teach you how to design in the circuit called solid state. If you don't, we don't have time. Here we're not dealing with how things work. We'll deal with that with a little bit, but and tell you what purpose they are. All we're trying to do is deal with symbols. If you want to understand, like motor controls uses these what we call ladder diagrams. So we're not going to get in here in this class and just explain how these things work. If you want to understand how they work, you need to take the what class? The motor control class, or the PLC class too. They'll cover those ladder diagrams there. But we'll just look at symbols and then we'll say what their function in life is. But as far as how to hook them up, how to design them, and all that kind of stuff. So no, you can't hook the Zener up either way. One way it acts like a diode, the other one it acts like a Zener. So that's a good question, but it's not. The book teaches things a little different than what I learned them for. And when I started looking on the PowerPoints, all the pictures that were in the textbook were not in the PowerPoint, so I'm going to go back and modify those a little bit. So this was an example of a book, and this is kind of a crossbreed of different types of drawings. So we have different types of drawings, and let me bring up another class where and y'all seen these things before. So when you go out and you buy a new TV, somewhere in that TV manual, close to the front, after you go through all the safety stuff, so they do that safety stuff in case you drop the thing on you, you're putting it up on the wall. And that's become normal just about any manual you get. The first part of the manual is what? Safety. I just bought a new electric toothbrush, and they got one of the books in there was a safety book in about 10 different languages. And then the other book showed you how to operate, told you how to operate the thing. So this is out of the class called Motor Controls. Yeah, maybe not. This is not the one. And this is symbols, by the way. So this is what I want to show you. So this actually came out of the book that came with one of my TVs. Is this a schematic? Yeah, this is a diagram, but it's not really a schematic. But what are they not using? They're not using symbols.
Oh, symbols. Oh, okay.
They're actually showing the what? They're showing pictures of the device. This is what I've always learned as a pictorial document. And normally when you go out and buy a commercial item that's sold to the average person, one thing they're not going to know is what? Symbols. So if you go out and buy a new TV, or you go out and buy a new DVD player or a Blu-ray player, it's going to have a pictorial diagram in there that's going to show you what? Pictures. And I refer to this is what I've learned as a pictorial diagram. This is not what the textbook teaches as a pictorial diagram. But to me, this makes sense when you call this a pictorial diagram because it represents everything with what? Pictures. So if I look at the only thing is not in color, So if I go back and look at the I/O section of my TV, they're in this order and they do what? They look like that. And it makes it real easy for me as a consumer to hook that thing up. Now I can't fix something if it breaks, but I logically know how to do what? Hook it up. But this is not a schematic. This is what we call a pictorial diagram. Because to use the schematic, then we wouldn't have pictures of the devices. We would have what? Symbols that represented the devices. Everybody okay? So this is one we show you in the motor controls, and I need to put that. I'm gonna move that over into this slide. Like I said, this class the drafting department used to teach this class for us, and then we realized they wasn't doing a lot of the symbols that we needed in our trades, in our program. So that's why we decided to take the class back over, because we couldn't require, drafting students to know all these electrical symbols. They could turn out to be an electrical drafting. That's not really what they taught here at the campus. They did architectural drafting, and then they did graphical information systems. So I would refer to this. This is kind of a crossbreed between a schematic and a pictorial diagram, because they're using pictures, but then they're also using symbols, and they're also using lines. You very seldom see this in the technical or scientific trade, because one thing, if I change the style motor, even though the motor does the same thing, and that's a pump, by the way, then my pictures wouldn't be right. So we do this over in motor controls. We have to inventory our lab stations, and then they say, do you have one of these? But then they draw a picture of it. The problem is, over time, the modules have changed, and then some modules they put out uses the IEC standard, the International Electrical Council, and then some of them use what we call NEMA standards, which is the National Electrical Manufacturers Association. And the NEMA is a United States standard, where IEC is an international standard. So what they had to do in their inventory sheet is they have to have two pictures, IEC or NEMA. So this is the problem we have with pictorial. It makes it a lot easier because now you got a visual, so you say, oh, there's that part over there. But normally, if you understand the symbols, then you'd still say, oh, that's that part over there, right? You understand? Electrical schematic using pictures. What page are we on? This is on page 6. And that's what they do. And they never give the answer in the textbook. Is this a schematic or is this not a schematic? It's kind of a crossbreed. It's using both pictures and it's also using symbols. Are we okay? Then we get into, they talk about some electrical symbols. I don't see it on that page. What figure are they talking about? Still don't see it. Oh, this is one. So the two symbols, the symbol they show in the textbook, you'll see these are these right here. And what does it say those are? It's on page 7. Huh? Yeah, but not just a receptacle, it's what we call a duplex receptacle. What do we mean by duplex receptacle? It's got 2 of them. So this is the standard receptacle that you would run into if you are wiring a house, right? We've got 2 versions of it. We've got a 20 amp and a 10 amp, but I'll show you a 15 amp will show you. Then beside it, I know it's real hard to see, it's got a number. And what the number indicates is what, y'all can't see this, this says panel box. You know what a panel box is? This is what most people call breaker boxes, but just about all electricians will call it a panel box. So that's where all your circuit breakers are. And if you ever look at a circuit breaker, we can look at that. But there's a listing in there, and beside each listing, every circuit breaker has a number. Now, the problem with electricians is that inside this building, we have people running air conditioning ducts. We have people running water ducts. And air conditioning ducts and water ducts have to go certain paths, right? But wire is flexible. What does it mean? We can go around everybody else. So normally, they put up the air conditioning duct. And now I can do this if I can read the prints, because I got to stay out of the way of an air conditioner. Right? I don't need to run my wire where a pipe's got to go. The pipe has got to go someplace. My wire don't have to. So normally on electrical prints, they don't show you the path of the wire. They just show you what circuit that sucker has to be hooked up to. And it's up to you to figure out the shortest path without law. Without knowing where the air conditioner does have to go. You know, you an electrician, you go in there and you don't understand the prints for the air conditioning people. And you go in there first and you do all this wiring. And they come in and say, buddy, you're going to have to move that wire. I got to put a bulb there. Right? Then what will you have to do? You will have to move the wire. Because they can't change the path they go. Right? You understand? But you can change the path they go. So you'll see on electrical prints, they show these wires. They don't show it going back to the panel box. All they do is say, this is what circuit this hooks up to. This means this goes back to the panel box, that arrow right there. This indicates how many wires are inside the raceway that you're going to run over to the panel box. But they don't show you how to get to the panel box. They just show you where it goes. So see, I know a little bit about electrical prints already. So that means I would have to come down here and I would have to put base plugs down this wall. They don't show me the distance between those. Why don't they show me the distance between those? Anybody know why? It's in the code. The code says if we have a wall that's over 8 feet long, we got to put a base plug every 8 feet. Okay. So they don't tell you how the location of them. You just got to make sure you find some type of stud or something you can mount them on within the limits that the code says it's supposed to do. They just say, okay, I want this many base plugs down this wall. That makes sense? So, you know, an electrician has to know a lot of stuff, symbols, but also they got to know the way the National Electrical Code tells them what they're supposed to do. By the way, National Electrical Code is not law. Y'all know that? Who determines how things have to be done? Electrically. Anybody have any electrical classes? It's what we call the authority having jurisdiction. So Jefferson County has electrical inspectors. The group of inspectors here at Jefferson County, they determine how things are supposed to be. And normally, every time I know of them, they adopt the NEC. So they don't have to. Everybody understand that? So if you're an electrician, you need to find out, usually when a new code book comes out, they don't adopt a new code when it first comes out. So that's one thing you need to find out too. You need to find out what code book you're under, right? what code book are they doing? And why they don't do that is they take time to go through it and see if the changes they made in the code is not what they think needs to be done. Like how many, I think Birmingham limits the number of duplex plugs you can put on any one breaker to 10, even though that's not in the National Electrical Code. So they show you they don't show us any switches here, normally, and we'll look at these. What they do on electrical is they put a little S over here. Y'all can't see the little S? What do you think S stands for? Switch. So they don't use the symbol that they're showing here. They put an S on the wall. And that means you got to put a watt somewhere on that wall. Got to put a switch. And they'll put some nomenclature on there to show you what it belongs to. Everybody okay? Any questions? And this is all they do on here. They show a couple of, and like I said, I'll try to integrate these into the PowerPoint. Where's my picture at right here? So they call this a pictorial drawing. And this is not what I learned a pictorial drawing was. But what we'll do is we'll use what the textbook says on the test. When's the first test? Yeah, we might have to move that a little bit because Nancy has the course set up, so once you finish a certain chapter, you take a test, so we might move it, but it should be okay. Pretty close to it. I think it's going to move to the Thursday before that because of the way the thing is set up. This is a pictorial diagram of a fluid system. So to get work, we have to cause things to move. Everybody understand that? So to get work, what we call watts or what we call, if you took a chemistry class, you probably learned that work is equal to force, time, distance. So to get work, you have to cause something to move. So my little watch hand talks to me one time, tells me to move because I'm not doing any work, so I'm not burning any active calories, right? So to get something to move, so to cause work to happen, first of all, we have to have some type of pressure, right? And then we push that pressure against something, and that creates a force. And then force is something that tries to cause something to do what? To move. Everybody understand that? And how much force you generate would be equal to how much pressure you have multiplied by the surface that you're pushing. Make sense? So force, that's a real quick formula. So it's a real hard formula. I don't know if y'all can get that or not. So force is equal to area times pressure. So that means in any system that we're going to get work with, we got to cause something to move. We got to generate a pressure, right? And of course, in electricity, voltage is pressure. So the more voltage we have, the more pressure. And when we push that against something, we cause that something to do something, right? Everybody okay? Now in fluid systems, fluid is anything that basically will move. Of course, so electricity is fluid, but we don't call it fluid, we call it current. So the two types of fluids we have is we have gases and we have liquids, right? Gases, we refer to those as pneumatic systems. So what we do is we move gases. Of course, the predominant gas we move is air. course, air is a combination of gas, but it's still gas, right? What's the advantage of using air? Exactly. I don't have to pay for air, right? So pneumatic systems are very, very popular because the gas is free using air. Hydraulic systems we use liquid. So we was going down to the beach during the break, going down to there, we got that little lake, and we go water, right? It's just sitting there on the steam. That's hydraulic. What's causing that steam? Water, right? A liquid. But the liquid has to be in motion, right? Our rivers, they create a lot of pressure, a lot of hydraulic pressure, pushing against an area. You know, they talk about this. People get swept up in their cars all the time. And to them, it don't look like, you know, they're moving through a rapid flow of things. And when it starts pushing up against the side of that big old car, you have a lot of area. But you push it against, 20 feet, you got 30 pounds of pressure, and you got a lot of weight there to move. So this hydraulic system, of course, what we have to do is the big advantage of pneumatics over hydraulics is that we don't have to have a tank to store our liquid in. Hydraulic systems, we got to store them, right? So in a hydraulic system, we have a reservoir or a tank, and then we have a pump. And what does the pump do? Well, the pump creates a difference of pressure. So it creates a low pressure on one side and a high pressure on the other side, and then the fluid moves from high pressure to low pressure. Then it goes out and flies through some control valves, and then this goes up. We call this an actuator. So an actuator is a device that takes pressure, takes a force and converts it into motion. So all motors are actuators. In electricity, though, we don't call them actuators, we call them motors. But in fluid power, we refer to these things as actuators. And then what do we have to do? We have to have something to get the fluid from, or the gas or what, from the pump to the load, right? Which in this situation would be the actuator. Everybody okay so far? And this is where what we call piping comes into play. And of course, you have to have certain gauge pipe, you have to have certain tees, you have to have this. Someplace you might run a big pipe, but you don't need to run that. Your main line might be a big pipe, but when you go out to individual devices, you might use a smaller pipe, right? What advantage does a smaller pipe have over a big pipe? Cost, right? And so you want to use the right gauge pipe to do what it is. So we got all these symbols that we have for the plumber or whoever's running the piping, come in there and know where the reducers go, to know where the universal joints go, to know where this goes, to know where the T goes, right? You understand that? So symbols. So if you're a plumber, you got to learn how to read symbols. And of course, we basically try to teach all three of these crafts, or give you an introduction into them. And you got to understand about symbols. We have standard symbols, and then we have companies, right? But what can the companies do? Well, they can create their own symbols that are used internally, right? Y'all understand that? So it's up to the company when they draw a print whether they use standard symbols or they use what? Their symbols. It's just like integrated circuits. Integrated circuits have all these part numbers and everything else. If I'm a company like IBM, and I want to order a million of this money, and I don't want Intel's part number put on there, I want my IBM number put on there. What's Intel going to do? They're going to put your number on it. You understand? Because you're ordering such a big quantity of these things, they'll put anything on the chips you want to. So now when you look at, if you don't have the schematic, and look on there, it's got an IBM number. It's really a standard Intel number, right? It's 7400 series. but it's got an IBM and a logo and all that other kind of stuff on there. And that's one thing having these schematics really help. So these are actually basic drawings of the device. Now a pictorial diagram, the way I learned it, they would actually have pictures of it. I mean, true what? Pictures instead of drawing. But this is okay. These are still pictures, but they're just drawn pictures. So I know this is a cylinder. I know it's what we call a double acting cylinder. Of course, I know this is the pump. I know this is the tank. I know this is the pressure relief valve. Just about in any fluid system, you know, fluids create a lot of pressure. And these are going to be pipes. Well, pipes are designed to handle a certain pressure, right? You understand that? And if you exceed the pressure of the pipe, and the higher the pressure rating on the pipe, the more the pipe is going to cost. That makes sense? So I'm trying to use a pipe that'll hold that stuff in, but I've got to, if something happens to my pressure regulator, something happens to my pump and this thing goes crazy, then we have a pressure regulator. It's just like on your water heater. So you have a fluid, you have a hydraulic system, right? You're pushing water through pipe. But that water heater has a pressure relief valve. Because when water gets heated, what does it do? It expands. If it expands too much. Did y'all see the Mythbuster episode where they plugged up the pressure relief valve and everything and torched those water heaters? One went out through the top of the ceiling and went up about 300 or 400 feet when that sucker blew up. So those things are dangerous. So don't jump out your pressure relief valve on your water heater. Please don't, because you can do it. This is what they refer to as a combinational drawing. I would refer to this as a combinational drawing. But what they're doing here is they're actually showing the internal works of the pressure regulator. This looks kind of like a pressure relief valve. It could be a pressure regulator. They have the ability to share the same function. So what you have is you have a calibrated spring in here, and you push this. This is going to add tension to this valve. If the pressure gets up too high, it's going to open up and then vent it out to air, which is basically what a pressure relief valve does too, but it's basically what a pressure regulator does. Why do they call this a combinational drawing? I guess that could be. This is a piping diagram, single line piping diagram. Now it doesn't really make any sense, but if you understand this, all they're trying to do is represent symbols. So this would tell me I need to put a what there, an elbow. This would tell me I need to put what they call a globe valve, which is basically a valve. This is where we need to put a cross, but on this side, this is what? Plug. This is a union. You know what a union is? A union is just a joint that makes things easy to take off. So if you've got a water heater, odds are in the life that water heater is going to go bad. If you've got everything soldered into your pipe up there, soldered in, so to do that, and the only way you're going to get that sucker out is to cut it. So what they'll do is they'll put unions between the pipe that goes down to the water heater into the pipe that goes up to the valve. And then what you can do is you can disconnect your union. Then you can unscrew the pipe out of the water heater. Because if it's soldered into the pipe, you can't unscrew it out of the water heater because it's threaded down in there. That makes sense? So a union is just something we use to make things easy to do piping easy to take out and put up. You go down and look for these at Lowe's. I don't know what a lateral is. Anybody know what that is? Looks like it's just kind of a T with an angle on it. Then this would be a 90-degree elbow. Basically, elbows are available in two angles, a 90-degree and then 45-degree. So here, notice they didn't give you that because it's obvious. Here they tell you. A bushing, a reducer, a check valve, a coupling, a T-fitting. So if I was a plumber, then I would know what parts, right off the bat, if I looked this, what would I know? I know what I would need to build this, right? Unfortunately, they don't show links, so you have to go out there and do some measurements to figure out how much pipe you need to buy. And then I'm not going to buy more stuff than I need. Right? You understand? So I'd go out and make some measurements, figure out how much pipe I needed, and then I know I need one elbow, I need one globe valve, I need one gate valve, I need a union, I need a crossover, I need a lateral, I need a cap on this end so I can expand my system later on, I need a belbow, I need some bushings, a reducer, a check valve, a coupling, and then a T. And then I know exactly what I need to buy. Right? You understand? And I think we're getting it. How much do we have to go on this? This is what they call a two-line drawing. So basically, it's basically using two lines. And you can now it makes sense to me because I can actually see what these devices are, and I know what a globe valve is, I know what a crossover is, I know what a union is, I know what a lateral is, and a cap, and a bushing, and a reducer, and a check valve, and a coupling. But the problem is the more detailed I make the drawing, the bigger the drawing is going to be, right? You understand? This helps me out because I'm not in plumbing. You know, plumbing. I do a lot of plumbing in my house. One of my least favorite things is plumbing. How many of you people like plumbing? I'm glad. Oh man, that and hanging sheetrock. I can do a lot of things, but me and sheetrock. I can hang the sheetrock beautifully, but it's the putty. Yeah, the putty. That's another name. What is this? What is this guy right here? Interpretation and flows usually produce an obvious sign. I don't know. Yeah, it is, but I don't know what the one on the right hand side was. I just scanned these, by the way, today. Well, I was doing that when y'all saw me in my office. I was trying to scan these. Yeah. And the book brings up a really, really, really good point. If something stops working, if a motor stops moving or a light goes out, then what have you lost? You lost your flow. Y'all understand that? So trying to go into a system and figure out flow just by looking at it is really, really hard. Unless you worked on that thing 100,000 times. Out of U.S. Steel, the electricians came up and get into what they call the apprenticeship program. They come up to the apprenticeship. So they actually, the only electrical, they didn't have any electrical classes at all. What they learned was what they learned. So a lot of them couldn't read print. So what most of the electricians did is they carried a book around in their back pocket. And if something broke and they figured out what it was, they would write the system and write what they would fix it. And that would get passed on. So you'd have these electricians out there, something would break, what would be the first thing? They would look at prints, what would they do? They pull that book out, they flip through the pages. Oh, this is what we did to fix that last time. And what did they do? They changed. But what if they didn't fix it? They'd call electricians. I call electronics. We did a lot of that troubleshooting there. So we'd go down there and we'd read plinks. We'd get our meter out, we'd read plinks, we'd get our meter out, and we'd say, okay, this is relay that. And then they'd come and change it. And then they'd add that to their book. So if they didn't really learn how to read print or schematics, they just. So y'all can see the advantage of that. So I'm not going to say you can't fix things without schematics. One of the main things you do when you troubleshoot, the second thing on the list is to look things over. Just look the system over, because a lot of times the problem is what? It's obvious. And you've got a hydraulic pneumatic system, and here's something out there going, you go out there and you got a broke pipe, right? Or you got hydraulic fluid all over the floor. You got a fuse going, or stuff like that. So a lot of the stuff you do without using schematics. But once you do that basic stuff, and you don't know how to read schematics, then you're in trouble. You'll never be a troubleshooter. You'll always be a part swapper. in the part shop. And we have people do that. They'll just start swapping parts. I went to work for a scale company, and they had all their scales were microprocessor computer based, and they had drawers full of spare parts. And so what would happen is that a scale would stop working, and they'd come in there and they'd start swapping out parts until it started working. And the one that they swapped out last, that's the one they threw away. All the ones between the last part and the first part, they put back in their spare part. So they pull it out, leave the new one in there, and put the one up there. And the problem is, a lot of times in electricity or electronics, when one thing goes bad, it causes what? Something else to go bad. So I got down there, and they had drawers full of bad parts. And now they couldn't troubleshoot anymore. Because why? The parts they were swapping out were bad. So they had about, I forgot how many scale units in there, those digital scales inside there that they could fix. And then they hired me, and I come trucking in there, and I could read schematics. And I got their spare parts slinging. That guy thought I was God. He prayed to me every night. Because I came in there and got him back in. I don't know if he's in business anymore. So if you have a problem in a circuit and it's not working, you got problems with what? The flow. Whether it's hydraulics, pneumatics, or electrical, or even electronics. By the way, this is in your textbook. I always love textbooks. We have two types of current that we have available in electricity. We have what we call direct current, and we have what we call alternating current. So direct current flows in one direction. This is what's created by batteries. Your car battery, your car uses direct current, even though it's got a device called an alternator, which creates alternating current. Right off the bat, they use an electronic device, we call them rectifiers, to convert that over to direct. Now, the advantage we have with DC is that we can electronically control DC. So your TV, even though you plug it into the wall, your TV is a DC device. Your radios in your cars are DC devices. Your cell phones are DC devices. Anything that's electronic runs off of DC. Anybody see the problem with this? Come on, people. Anybody had an intro? This is the symbol, by the way, for a DC source. Originally, it was a symbol for a DC battery. But now a lot of our electronics, a lot of our DC is generated electronically. So, you know, when you put your charger in your cell phone, it is DC. But inside, before the thing you plug into your cell phone and what you plug into your wall is a little low tiny box, right? You understand? They look like cubes. That's the device that's taking AC and converting it into the right DC that's needed by your cell phone. So if you took your cell phone and took that little old box out there, took off the wires on your USB plug and plugged it in out amount of power, that sucker would blow up in your panel. Because you're putting AC on the device that was required by DC. If you took the radio out of your car, you had a transformer at your house that stepped 120 volts down to 12 volts, and you plug that sucker in that transformer, that radio would disintegrate and would smoke because it's designed to operate off of direct current. The symbol of the battery is backwards. The symbol of the DC source is backwards. And so that means the current flow is backwards. So this is wrong. Make this correction in your textbook. So this right here, this one is the symbol for the negative. So the negative is the short side, and the positive is the reverse side. Now the problem we have with DC is that when it was discovered, so DC wasn't invented, DC was discovered. So DC is all over the place in natural form. They figured that something moved. And so they came up with these polarities, positive and negative. They assumed that the positive was the high pressure side.
So originally they thought that current flowed from positive to negative. That's still taught by some institutions. It's no longer taught by the government. If you ever hear anybody say conventional current, that is not what's flowing. What's actually flowing is the part of an atom that has the ability to move around. We see this all the time. It's these electrons that's moving out on the side. We can move them suckers out and get rid of them. We create what normally when an atom is balanced, the number of electrons you have in the shells rotating, and the number of what we call protons in the center, they have to match. And then the atom has no charge. If we cause that atom, if we cause an electron, we can't get rid of the proton that's in the nucleus. That's what causes atomic bomb, right? To split that nucleus. But we can cause the electron to leave. Well, if the electron leaves an atom, then all of a sudden it contains a positive charge, right? Or if an electron migrates into that atom, then the atom becomes charged. We call these ions. You see this all the time, static electricity. That's what you're causing to happen. You whip around in plastic and stuff like that, and you carry a charge. Well, how do you carry a charge? Whether the atoms in your body has either lost an electron or it's what? It's gained an electron. And if you got a charge, then things are going to move. But what's moving? Well, it was proved that what's actually moving is these electrons. Now, the problem with electrons is that to push them, when you like charges repel and unlike charges attract. Do you understand that? So what happens is the negative charge of your source is pushing the electrons, and then the positive is pulling them back. So this would be the direction of the current flow. Unfortunately, when they developed a lot of your solid state symbols, they still thought that current flowed from positive to negative, from high pressure to low pressure. They just didn't understand that the negative potential could be the what? The high pressure. They don't understand that. They understood weather. They understood low pressure and high pressure. But they don't understand that the negative push could be the push, right? You understand? So this is the way current flows in electronics. But they talk about conventional current flow. And some universities, by the way, still teach conventional current flow. And they teach it on the aspect that if you got electrons moving in one direction, and every time an electron moves out of an atom, it creates a spot in here that we refer to as holes. And so the holes are moving one direction, and the electrons are flowing the other. That makes sense? So conventional current teaches what they call hole flow. We teach electron theory. The only thing that I know as far as mathematically and your symbols, it makes no difference on your symbols. It's just that you got to understand that we have eras, and then on an electron flow, everything flows against the eras, right? But as far as mathematics, the only place I know it makes a difference is in magnetics. So y'all need to make that correction in your book. So they got the symbol wrong. And I published the book, and I understand it's a technical book too. And, you know, you have editors look at it, and people look at it, and then when you start teaching out of the book, you see flaws that you put in there. Even labs. I've been giving out labs for years, and then somebody will bring, well, that's wrong, or that's wrong, and, you know. Students, we have a tendency to see things we expect. So how are we going to make that correction in your textbook? So this is wrong. What's wrong? You can do one of two things. You can change the symbol. So what you can do is you can come up here and this would probably actually be the easiest way. Is put a short one out up here, and then make this one down here long. And then that would be the symbol of a DC source. It was originally the symbol of a battery. And what a battery is consists of cells. So these little D
these little D's you buy and these double A's and triple A's, those are not batteries, those are cells. But the problem is consumers didn't understand cells, so how do they label them? They call them batteries. But a battery is always more than one, right? So you make cells all the time. When you put two double A's in your remote, and you're creating a battery. Now, a 9-volt is a battery. So if you ever tear a 9-volt battery apart, you see it's got 6 little cells in it. So it is bad. And your car's got a cell. Your car's easy to see because normally if it's not a gel cell, you got one cap for each one, for each cell. So to be a battery, you got to have more than one. But now, they used to call them cells. If you went a long time ago, you'd see a battery was called a D cell. But people had problems with that. And they said, I need a battery. I don't need a cell. They lock prisoners up in cells. AC flows in two directions. Now, the advantage of AC, first of all, AC is a lot cheaper to generate than DC. So AC generators cost a lot less than DC. It just takes more to construct. So that was one of the reasons. And when this device called the rectifier came out, where they could take AC and convert it to DC, that's when they switched from DC generators in the car over to AC. Of course, they don't call them generators in the car, they call them alternators. So your alternator is making AC because an AC alternator would be a lot cheaper than the DC generator that would replace it. The diodes, these rectifiers, are very, very cheap. So real easy to take AC and convert it to DC. Plus AC, we can change the pressure level with these things we call diodes, with these things we call transformers. The problem is, one big thing, the higher the pressure, the higher the voltage, the more dangerous it becomes to us because we can conduct electricity. If we get current flow through our body up to like 50, if you get 50 milliamps or 0.05 amps through your body, odds are we'll talk to you about capacity. How much push, how much flow you have through your body determines on how much opposition your body has, right? And how much pressure you get in. So anything above 50 volts is considered to be a lethal voltage. So this is why you can go out on your car, you can play around with batteries and stuff like that. There is current flow through your body. You touch two potentials and you're a semiconductor and there's current flow through your body, but it's not enough current flow to hurt you, it's not even enough current flow for you to feel that, right? But the advantage we have on higher the voltage is how much flow we have to generate our work. So how much work we get, we call this power, is equal to V times I. And V would be the pressure. This is how many volts we get into. And this would be what we call the current. And the current is the flow. So the more current you have, the faster it's moving. So you see these all the time on vacuum 8.8 amps and stuff like that. Well, that's how fast those electrons are moving. 1 amp would equal to 6.25 times 10 to the 18th electrons flowing by a point in a second. So we don't give you so that's just a rating, right? But the more amps you have, the faster the flow. The faster the flow you have, the more work you have. Because work is equal to force times distance. And distance and speed are directly proportional. So the faster you go, if you double the speed, you double your distance. So we could also say work is equal to force times speed. And that's what we use in electronics. So we take the amount of force we have, we multiply it by the amount of current we have, and then that would give us the law. That would give us how much work we get. Now there are some changes. The problem is, the higher the voltage, the more dangerous it becomes to me. But we have another formula where we try to transmit power, where how much current is required is equal to the power divided by the voltage. Using symbols, right?
Now, how much current I can get through a pipe? What determines how much water you can get through a pipe? How much water you can get through? So when I go out to my house, I can buy a 4-inch pipe. I can buy. No, that doesn't determine how much water you can get through. The thickness of the walls determines the pressure, but that doesn't determine the flow. What determines the flow? The size of the pipe. So it means a 3/4-inch pipe can handle a bigger flow than a 1/2-inch pipe. So in electricity, we use these things we call conductors. What determines how much current you can push through a conductor? The size of the gauge. The size of the conductor. Right? You understand? Okay. So that means the more current I push, the bigger my conductors have to be. So that's why you go and look at the wires going to your radio. You go out there and look at the wires going to your battery. Which one is the biggest? The battery. Why? Because it has to push more current, right? You understand? The problem is when we push current through a conductor, it's going to lose pressure. It's just like your blood system, right? You understand that? So what Alabama Power is trying to do is they're trying to push as much power as possible with the least amount of current. So what do? Well, it says the amount of current I need is the power, and you don't pay a voltage bill. You don't pay a push bill or a current bill every month. You pay a power bill because power is work. So Alabama Power is not trying to sell you a pressure or a voltage. They're not trying to sell you a current. They're trying to sell you power. And how many people live next door to a power plant? Where are these power plants at? Well, I got one in Wilsonville, right? But you Gaston. This college right here gets its power from the Tennessee River. This is TVA River. Well, how in the world can they get that power to Lawson State Community College? Well, they could use conductors that are almost as big as this room. Or they could raise the voltage up real high and use smaller conductors. You understand? Because current is equal to power divided by voltage. So the higher I make that voltage, the less current it's going to require. The less current means I can use smaller sized wire. Instead of using copper, now I can use aluminum. Aluminum has more opposition, but aluminum is a heck of a lot more cheaper than what copper. So what we can do with AC that we can't do with DC is we can step the voltage up for transmission with these things called transformers, and we can step it down to make it safer. So I can start getting, instead of being 50 feet up in the air, I can get it down to 10 or 15 feet. Or I can put a down drop coming from my house, and that stuff is looking for ground anyway, right? You understand? And not have it arc to somebody to get it. So Alabama Power can step it up to all these different voltages, up to 500,000 volts. So I imagine coming down from Tennessee down to Bessemer, they're using probably a 500,000 volt line. So that means they could send 500,000 watts of power with 1 amp of current. But I cannot get 500,000 volts into my house because it would arc the ground, right? Fry you. So they start stepping it down to make it what? Safe. We can't do this with AC. So one of the biggest advantages of AC is we can change the voltage level with these things called transformers. We can step it up for transmission, step it down for use.
So transformer change the voltage on one road.
Yeah. So transformers don't change power. So this is theoretically, if transformers were 100% efficient, then we come over here and I turn on a 100-watt bulb, then the plant up in Tennessee would have to provide me 100 watts. So when it goes to the transformer doesn't change power, it changes voltage. So if it steps the voltage up, then the current drops down to produce that power. But the higher voltage means I can send it further, but now it becomes very, very unsafe, right? So what do we start doing? We start stepping it down until it gets to my house. And this is why you have two voltages at your house. You have 240, you have 120. So all your high wattage devices runs off 240, which means they can use smaller conductors to get it there. Now I can run those conductors through the wall instead of having to run them outside the house, right? So you have 240 is for your high wattage devices. 120 is for your safer device. Now 120 is still lethal, but it's not real lethal. Now, I don't know, probably everybody, sooner or later in your lifetime, you're going to get shot by 120. Odds are it's not. 120 volts, to get killed by 120 volts, it's got to catch you in the right situation. 240 volts is really, really dangerous. So that's the advantage of AC. AC motors are a lot cheaper than DC motors. AC can be stepped up and stepped down, but it's real hard to electronically control it. What do? Well, we take the AC, convert it to DC. Your TV runs off DC. Your microwave probably runs off DC. Your cell phone definitely runs off of DC, right? So your stereo runs off DC. If you got an entertainment system in your house, it runs off DC. If you got a computer in your house, it runs off. Your cable box runs off DC. Your DVD player runs off DC. But we have that unit in there that takes the AC and converts it over to DC. So we can transmit it with AC, and then we can convert it to DC when it comes time to use it. And this is why they went from what? They went from generators over to DC generators over to AC generators. Because AC generators, for the same wattage output, AC generators are a lot cheaper. The AC motors are cheaper per horsepower. So that's why used to the advantage DC motors had over AC motors if we control them precisely, get exactly the speed and the torque characteristics we want. Then they came out with an electronic device they call a variable speed drive, which is electronic, it's DC. So they take DC, AC, convert it to DC, then they electronically convert it back to AC to change the speed of the motor. The variable speed drive. It still goes from DC so they can do what? So they can electronically control it. So these variables, some people call them variable frequency drives, but they're actually variable speed. So AC goes back and forth, 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 back and forth. The electron, so DC, if you turn DC on, and these guys move about at the speed of light, that means these electrons are just making loops, right? By the way, voltage sources do not create electrons. It's moving the electrons that's already in the system itself. Okay. All the voltage source does is create a difference in potential, which causes these things to move. But batteries don't make electrons. They just cause electrons to move. Okay, you understand that? In AC, odds are the electrons, the only electrons are going to be the ones that are at the loads. The electrons at the source never make it to the load. Because they're doing what? Yeah, there was a demonstration where a guy had a bicycle and he had a wheel there that represented an electron. He said, this is DC. You see the electrons flow all the way around the chain. He said, this is AC. He went back and forth, and the electrons are just doing what? Yeah, they're not. So the electrons at the source are not going through the load. So the same electrons are being used by the what? By the loads all the time. So this is a symbol for an AC voltage source. Whether it's an electronically produced AC or whether it's done by a generator. We can electronically produce AC. How many have an inverter that they have in their car? Yeah. My wife's van's got one built into it. So she's got a regular 120 volt socket in the back on her van, which is pretty nice. So we can, but it's DC and we can electronically control it, so we can use DC to create AC. By the way, stereo sound is AC. So that's what your radio is doing. It's taking DC and then generating AC. So the output of your speakers is an AC. So y'all gonna make that correction, right? Single line drawing, electrons flow, negative, positive. Everybody okay on that?
Everybody okay on alternating current, also called AC? So AC stands for alternating current. DC stands for direct current. Direct current is current that is moving in one direction. All your batteries, solar cells, create DC. If you got a solar cell, the price of those things are starting to drop down, which will be neat when they get low enough so we can power a house on it. There are some houses that do that, ones that are way up in the mountains and stuff like that. But what they do is they use the solar cells to charge the battery. And they take the batteries and run it through this thing called an inverter. And the inverter creates AC for their house. Yeah, those inverters are nice. Huh? Windmills, it depends on how the system works. The big wind farms, a lot of times what they'll do is they'll store energy in batteries. Even Alabama Power does that. Big buildings. Alabama Power's building up in Birmingham. I had a tour of that. They store electricity, but they store it in the form of freezing water. So they freeze water, and then they run it backwards through an inverter and turn that back into electricity. And what they do is they freeze water during the night when the demand for the building is real low, and they use it during the day. So their demand for that big building down in downtown Birmingham is basically flat over the entire 24-hour period. And that's what they like. Yeah, they freeze water. So during the day, they freeze water. During the night, they freeze water. During the day, they evaporate it, and they use the evaporation to create energy. So they got this big old icebox room downstairs, which is really, really big. And then they have big old backup battery rooms for their big computers up there that controls the power grid. So they take the line and convert it over to DC and store it in these big old battery things. That's very impressive too. And then if the power ever fails, then it switches from the power over to the battery through an inverter. So your computers are still running off of plugged into AC. And that's the one big advantage of DC that we can't do with AC is we got that control over it. So we can take DC and convert it to AC. And we can electronically take AC and convert it to DC. Let's see what else we got on here that's not in the PowerPoints. The direction. In electronics, normally we don't show the direction of the current. Because if you got enough sense to read the symbols and to read the schematics, you know the direction. AC, we don't usually indicate the direction of current. AC is considered to not have a polarity because the polarity changes so fast. So Alabama Power changes directions 120 times. I'm sorry, 120 times per second. So that means that sucker's changing polarities every 8.3 milliseconds. 8.352 milliseconds. So if it's changing polarities every 8.353 milliseconds, then AC really doesn't have a polarity. It's only there for a short amount of time. DC has a polarity. You've got to honor most electronic devices are designed to run on a certain polarity. Now we have things that have the ability to safeguard you. So if you go in and you've got your remote for your TV and you put the batteries in backwards, there's a little check valve in there called a diode that doesn't let it come in and burn up your remote. But your remote will not work. If you put one battery in right and one battery in backwards, they just cancel each other out. You don't hurt the batteries, it's just that nothing will work. So electronic devices have to have a certain direction currently. So if you go out there on your car and you can do it if it fits. You can take the black lead and hook it up to the red lead. And you can take the red lead and hook it up to the black lead. And
hopefully there's a fuse in there that's going to get it, or you're going to burn up a bunch of stuff in your car. Your radio, your compressor, and everything, because these guys are designed to run on what? A certain polarity. That's usually why they have a fuse. Not going down to your starter. Your starter would turn in the wrong direction. So your starter would try to crank your engine up in reverse. And odds are you could do it too. Which wouldn't be good, would it? So here what we do, here what they're doing is they're showing and even in pneumatic systems, normally we don't show flow lines because we know that the flow is running from the compressor to the field, right? You understand? But they could be in there. Very seldom will you see these on electronics because they take for granted if you got enough sense to look at the schematics, you have enough sense to. We've already looked at that one. Already looked at that one. Already looked at that one. I don't have 1-15. This is showing us a I don't know if I can get this up high enough to show it on camera. It's going to be close. So this is could be fluid, could be pneumatic, could be hydraulic. And what we have is we have a directional control valve. So y'all understand, if we got flow, we have the ability to control the flow. If you can't control the flow, you got problems. Like, we have a flood, you got water running all over the place, and you're not controlling that stuff. What does it do? Now, we have high winds come through, and we're not controlling the flow. It blows stuff down. So when we create the flow deliberately, then we need to have the ability to control the flow. Either to control the amount of pressure we have, or to control the rate of the flow of the fluid or electrons. So in fluid power, we have pressure control valves where we can control the push. We have like this. So in electronics, one of the things that we use in electronics while we learn how things work, instead of having actual devices, we let the students construct a lot of circuit. And what do they construct it from? Well, they construct it from a schematic. So we have a lab book where they construct the circuits, and then we construct it on a unit that we call a trainer. So this is our trainer right here. It's taken out of the bag. The trainer itself. And what we have is this is the actual schematic for this trainer. And the problem we have is that a lot of companies don't used to, when you went out and you bought when I built my stereo up, you bought that stereo, they gave you the schematic. I got 2 big amps, and I've got the schematics on because they provided it with the stereo. I got a big nice reel, which is out of date now. But I've got the schematics on it, right? So if they do break, I can keep them fixed. Now when you go out and buy a TV, you don't get a one. In fact, if you work on their TVs, you have to sign a disclosure saying that you will not give those schematics away. Because, used to only a few people made TVs. But this is the schematic for this. And of course, this is not the power section. Here's the power section. No, I don't have the power section. It must be 3. But if you understand these symbols, I'll go back and look. Undoubtedly, I didn't get it. So I don't see the power supplies on here. Then I can take this and relate it to what? And I can fix this. In fact, this was bad. This was bad. I don't know, right? Of course, but with a little troubleshooting, what's